Hi everyone, Dr. P here, and in this lecture video we'll take a look at standard enthalpies of formation. So why don't we start by looking at the graphite to diamond reaction again. So from last time we have carbon in graphite form reacting to give carbon in diamond form. Now remember, we can't get delta H directly as the process is too slow under normal conditions or too extreme under laboratory conditions. But we can get delta H from heats of combustion, which is what we did. Remember, let me grab the notes here, hold on. We burned things. So when you do a combustion reaction, the enthalpy is called a heat of combustion. And so we could get our values, or a value for the delta H for this reaction from using heat of combustion. So a similar method uses what are called standard enthalpies of formation. And you can see Appendix G for values. And maybe I'll pull out Appendix G and just post that as a separate PDF so you don't have to go wading through the whole text PDF. So what is our standard enthalpy of formation? Well, standard enthalpy of formation is going to be delta H F naught. That's N-A-U-G-H-T, naught. So the naught means standard conditions. And so it's delta HF, so delta H of formation, enthalpy of formation under standard condition. So this is, if we're going to define it, the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. Okay. Now, the naught is what signifies the standard states, and these standard conditions provide a convenient reference point for thermodynamic calculations and measurements. So, standard state definition. So, for a compound, the standard, I'm going to abbreviate standard, STD, standard state of a gas is 1 atmosphere, and that's exact. All right, the standard, a pure liquid or solid is just that, pure liquid or solid. And for a solution, the standard state is a concentration of 1 molar. And that's exact. So it's supposed to be a capital M there for 1 molar. And then for an element, the standard state is the form at which the element exists, or in which the element exists under conditions of 1 atmosphere and 25 degrees Celsius. Form in which element exists at 1 atmosphere and 25 degrees Celsius. And these are also exact, exact numbers. And you can get that from the periodic table. It usually, well, not all periodic, some periodic tables will actually indicate which elements are solids, liquids, and gases. Really, there are only 2 liquid elements at standard state, and those are mercury and bromine. There's some other elements that have really low melting points, but at 25 degrees Celsius they are still solid. So these are sort of the rules here and why we're using our enthalpies of formation here. So let's put them to use, and let's see what we can do with them. Okay. Example. NO2 formation. We have half a mole of N2 plus 1 mole of O2. These are gases. React to give NO2 gas. Our delta HF naught equals 34 kilojoules per mole. And again, this is per mole of product with the product in its standard state. We can look at methanol formation. Solid carbon plus 2H2 gas plus 1/2 O2 gas reacts to give CH3OH liquid. Delta HF naught equals minus 239 kilojoules per mole. And again, see Appendix G for some values. Now, the delta HF of these guys individually is 0. Delta HF for a given thing in its elemental form, or in its elemental form is 0. So we could actually use these. So the tables are compiled from these types of reactions. And so we can use these to get delta H for a reaction. For example, can use delta HF naught values to get delta H reaction. So, for example, we'll have CH4 gas plus 2O2 gas reacts to give CO2 gas plus 2H2O liquid. So essentially what we're doing is we are taking apart each reactant down to its elements and building up each product. So we would have CH4 gas is solid carbon plus 2H2 gas. And then 2O2 gas is just 2O2 gas. And these guys would combine to give CO2 gas plus 2H2O liquid. Okay. In a diagram, we could go ahead and look at this. We'd have our CH4 gas, our 2O2 gas. And let me make sure I have enough room here. And our CH4 will give us carbon and 2H2. We'll call this A. Our 2O2 gas will give us 2O2. We'll call that B. And then our carbon and O2 will combine and give us CO2 gas. We'll call that C. And then we'll also have H2, 2H2 and O2 combining to give us 2H2O liquid. We'll call that D. And these, of course, are our reactants. And these are our products. So it's a little hard to maybe follow things crisscrossing. But basically, what standard enthalpies of formation do is they allow us to break down a more complex reaction into fundamental pieces of formation, if you will, and we have tables of those standard enthalpies of formation. So let's look at these individual reactions then. We'll do the calculation. Maybe I'll keep this here for right now so we can see this. Get that in frame. There we go. Okay, so for reaction A, we have CH4 gas goes to C solid plus 2H2 gas. Well, this is the reverse of solid carbon plus 2H2 gas goes to CH4 gas, which is our delta HF naught chemical equation. We could look up delta HF naught, and that's minus 75 kilojoules per mole. So that means that delta HF naught for that guy is 75 kilojoules per mole. So we'll say for A. Now for B, we have 2O2 going to 2O2, so our delta HF naught is 0. 0. Okay, because there's no change. Now we have C is C solid plus O2 gas reacts to give CO2 gas. So our delta HF naught equals minus 394 kilojoules per mole. And the formation of water is H2 gas plus half a mole of O2 gas reacts to give H2O liquid, and delta HF naught equals minus 286 kilojoules per mole. But D is 2H2 gas plus O2 gas, reacts to give 2H2O liquid. So this is 2 times formation equation. So that means that delta HF for this guy, delta HF naught, has to equal 2 times our delta HF naught for H2O. So our delta H, and I actually shouldn't call it delta H F naught, I'm just going to call it delta H naught, is going to equal 2 times delta H F naught for water, which equals minus 572 kilojoules per mole. Okay, so our delta H for our reaction delta H naught for the reaction equals delta H naught for A plus delta H naught for B plus delta H naught for C plus delta H naught for D, and what that equals is 75 kilojoules per mole plus 0 minus 394 kilojoules per mole minus 572 kilojoules per mole, which equals minus 891 kilojoules per mole. And we can actually look at this and see what our overall we could compare this to our actual measured heat of combustion, enthalpy of combustion for our methane reaction, and find that the two are actually pretty similar. Okay, so in summary, we can say that the enthalpy change for a given reaction can be calculated by subtracting the enthalpies of formation of the reactants from the enthalpies of formation of the products. Or we'll just write out the following equation. Delta H naught for a reaction equals the sum, so I'll use the capital Greek letter sigma, the sum of the number of moles of, the number of different products. Anyway, the sum of the delta H F naught of the products minus the sum delta H F naught of the reactants. Here the N refers to moles because remember, here we had to multiply by 2. So it's not just that we're adding heat of formation of water and CO2, we have to add 2 waters. So it's heat of formation of CO2 plus 2 heat of formations of waters minus heat of formation of the reactants. And so don't forget your stoichiometry. All right. Phew. Okay, so that was heat of formation, or standard enthalpies of formation, I should say. And we'll practice more on this in class. But until then, stay safe out there. Bye now.